Okay, we're going to look at the last problem on the final examination. I'm going to do an example problem with cycles to 0. And then so we're going to have 140 ohms here, 120 ohms, 120 ohms, 120 ohms, 140 ohms, and a 0.02 amp current source and a 10-volt voltage source there. Let's put that plus and minus there. Now, we want to get that Thevenin equivalent voltage, which is the voltage at point A when there's no other loads on there. So I want to get voltage at A. Notice, because we have a ground here, the voltage at A, by just looking at a voltage divider here, it's halfway between C and A. So VA is equal to VC over 2. So that's the Thevenin voltage. Is going to be half of VC when there's no other load connected. Now, how am I going to get this? I'm going to cut this and do this in parts, and I'm just going to cut this right here temporarily and just look at this 0.02 amp current source and the 140 ohm resistor. So that's right here. There's point D. That's where we cut it. Well, that's on D, that's on ground right there. D is right there. Here is D. So that's going to be equivalent. This is 140 ohm resistor and a 220 milliamp current source. That's equivalent by Thevenin Norton equivalence, which V Thevenin is equal to I Norton times the resistor equivalent. Well, so let's see. 140 times 0.02 is 2.8 volts and 140 ohms there. Now, we're going to add on to that. So that's the part left of point D. I'm going to add on to that because I'm really interested in point C. I'm going to add on to that the 120 ohm resistor there. So this circuit is to the left here is equivalent to a 260 ohm resistor and a 2.8 volt voltage source. Well, what's that equivalent to? Let's get the Norton equivalent to this 2.8 with 260 there. That is, let's see, take 2.8 divided by 260. That should be 0.0177 amps. So everything to the left here is going to be equivalent to this current source and 260 ohms. Now, let's take a look. So I've cut it right here. Now let's take a look at this side. And I'm just going to look at the 10 volt and the 140 ohm and get the equivalent of that, the Norton equivalent. Well, I'm going to take the 10 volts divided by 140 ohms. So this part, just this part right here, is equivalent to a 0.0714 amp, that is 10 volts divided by 140 ohms, 0.07 amp current source, and 140 ohms in parallel like this. Now, we're going to add this section here, which is 120 ohms, 120 plus 120, 120, 240. So I have a 240 ohm. That's the green part going around here. Green part going around there. And 140 ohms. That comes from here, but in Norton, so it's parallel. Let's see. So I want to get 140 ohms parallel with 240 ohms. That's going to be 88.42 ohms, the equivalent of 88.42 ohms. Now, I'm going to add these together. I'm going to add this one and this one. So what we're going to get then is we're going to add the current sources there. 0.07 plus 0.01 is 0.0822 amps. And we're going to have a 88 ohm in parallel with a 260 because I'm adding that on. So that is, let's see, 88.42 in parallel with 260 ohms is 65.98 ohms. So, and point C is up here. Let's see, here's point C, point C. I just added those together. So point C is like there. Well, let's see that this is the sum. Remember, this is the sum of these two. And this is 260 in parallel with 88.24 is 60, almost 66. So let's get the Thevenin equivalent of that. This is going to be, let's see, 0.082 divided by 66 is 5.42 volts, and that's 66 ohms. Well, that's going to be what is voltage C when there's no other load on the den? Voltage C is just going to be this 5.42 volts. So that's voltage C. Well, divide that by 2, and we're going to get, let's see, voltage A is equal to 5.42 volts divided by 2. Let's see, what is that? 2.71. 2.71 volts. Okay, that is voltage A. Well, voltage A is the Thevenin voltage, 2.71 volts. That's the Thevenin voltage for that circuit with psi equals to 0. Okay,